Welcome to PDC, everyone. Thank you very much for coming. My name is Hazem Shafi, and I'm a principal architect on the parallel computing platform team at Microsoft. We are thrilled to be here. We have a lot of things that we're building for you, and this is the first time that we're going to be able to share it with you and show you the fruits of our labor, and most importantly, get your feedback, good and bad, about what we're doing. The subject of my presentation today is parallel computing, and specifically the tools and programming constructs that we're giving to you in the next version of Visual Studio to make it easier for you to develop, debug, and tune parallel applications on Windows. So there's a lot of great stuff in here. I won't be able to cover everything. There are 4 sessions that our team is giving at PDC. Throughout my presentation, I'll be giving you pointers to those presentations. In fact, there's one immediately after this one at 3:30. So I'll make sure to do that while I'm going. OK, here's a quick outline of what I'm going to cover today. A very brief motivation for why this is an important area for Microsoft to invest in, why this is an important area for Visual Studio. And the way I'm going to do this is instead of just showing you demos and jumping back and forth between various tools and programming techniques, I teach a class on parallel programming at Microsoft. So I chose to do this to basically take you through a parallel application development process, a very basic one. And at certain points when it makes sense, I'm going to show you a demo for tools in Visual Studio that help you in each one of these steps. So this is the approach that I'm going to take. And then I'm going to show you what we're doing on the programming side to make it easier for you to express parallelism. So you don't have to create threads yourselves and worry about managing the threads and breaking the work among these threads and synchronizing, etc. And then finally, we're going to show you a brand new set of parallel performance analysis tools that we're also shipping in Visual Studio 2010. So let's go ahead and start. A key point that I'd like to convey to you is that Visual Studio 2010 has a lot of features specific to parallel programming. We are going to give you programming libraries and constructs that are going to make it easier for you to express parallelism, to write the code, both for native and managed code. We also have debugging support for these new techniques so that it's easier for you to debug these new applications. And finally, we're going to ship performance tools that help you diagnose problems like synchronization, inefficiencies, UI glitches, things like that that have been really difficult to do in the past. OK, so let's start with the motivation. Why is this an important problem? I'm not going to spend too much time on why we're here today. Why are we in this multi-core processor era? The most important points to remember, though, that now and today is that single-thread performance is going to be relatively flat in the foreseeable future. So we no longer have the free lunch of a doubling in performance every year and a half that we used to have for free, basically, in the past. And what that means to us as software professionals is that the performance burden has been shifted to us. Now, we have to do more work now in order to exploit the latent performance that exists in these processors. And if you're interested in enabling new experiences in your application, then you will most likely be forced to exploit parallelism in order to both deliver those experiences and deliver them at reasonable performance. So of course, this is a major concern for Microsoft, right? As the largest software company, we are definitely interested in helping you develop parallel applications easily on Windows. So we're interested in how you code the applications. We're interested in how you debug the applications and how you performance tune them. And we're trying to tackle all of these areas in the next release of Visual Studio. Visual Studio now has a team called the Parallel Computing Platform team, and that's the team that's basically delivering on these features that I just described. So the good news is that there's help coming your way in the next release of Visual Studio. And in the talk, I'll cover a broad range of things. I'll drill into certain areas. I'm the performance tools architect, so I'm going to spend a fair amount of time talking about the parallel performance tools. But I'll also show off some of the other things like parallel programming libraries that we're shipping. Here is the stack that my team is delivering. We are delivering tools that are shown in blue on the native side. Things like the parallel pattern library, agents library. We also have a runtime system that takes care of scheduling parallel work behind your back. On the managed side, we have a parallel version of LINQ. If you're familiar with language integrated query, we now have a parallel version of that. It's relatively simple to express. We also have a task parallel library that makes it very easy to parallelize some very common constructs in .NET applications. And on the left-hand side, in this pink or purple, we show you the tools. We have debugging support for these programming constructs, and we also have parallel performance tools that we're shipping in Visual Studio 2010. OK, so let's start talking about a very basic parallel application development process. Parallelism, of course, is about performance. So the very first thing we have to deal with is we have to understand the performance requirements of our application. That's step number one. You have to have a good idea about what your performance goals are. And you have to map those goals to the various scenarios that people use your applications with. Once you've identified these performance goals, the next step is to measure your existing performance. So here I'm assuming that you already have something to measure. Right? If you're developing a brand new app, of course you'd still want to measure it, but it's going to take some time before you have enough code to make some measurements. So the next step is to measure. Make sure that check whether you're meeting your performance goals. If you're not meeting your performance goals, then you have to go through a performance tuning step. And we recommend going through this performance tuning step with the existing code base, with the sequential code base. And I'll get into all of these steps later on. If you've tried to tune and you still fail to meet your performance goals, then you have to start investigating whether there's parallelism in your application that you can exploit to meet your performance goals. And finally, if that really is the case, then you code to exploit this parallelism. And then you run, measure, and tune. And you can do this full cycle now in Visual Studio 2010, which is really great. So let's talk about goal setting a little bit. The very first thing, and so I'm going to share a lot of stuff that we've learned in-house. Right? We have people who do a really good job setting performance goals. They run performance regression tests in the lab for every build. But sometimes we still ship products that do not meet our customers' needs. And one big reason for that sometimes is people do not use realistic data sets. You have to make sure that what you're testing in the lab really reflects a significant majority of your clients out there, of your customers out there. Toy benchmarks just don't work. The other thing that's really important when you're measuring your performance is to understand the ecosystem. Is your application going to be running on a system by itself? Or are you going to be sharing the system resources with other apps? So for client applications, of course, you're going to be sharing the system with a bunch of other things that are typically running, right? If you're a server app, then you might be lucky, and you might have full access to all the resources. You have to think about all of these things when you're trying to understand the performance of your app. Now, a key thing that a key piece of advice that we give people is don't parallelize unless it's absolutely necessary. So if you're able to meet your performance goals sequentially, you're in great shape. You should do a couple of things, though. One is you should plan for parallelism in the future, because it's going to be inevitable. At some point, your data sets are going to grow with time. or you might add new features, and you're going to be forced to parallelize. That's basically the way it's going to be for the foreseeable future. So by planning for parallelism, here's what I mean. The worst thing that you can do is have a sequential application that's very painful to parallelize. So you have to think that in the future you might have to parallelize and account for that inevitable fact, most likely, for most of us. You don't want to have to rewrite all of your code when it's time to parallelize. So that's something to keep in mind. The other reason why we give this advice about not parallelizing unless you have to is because parallelism comes with complexity. It adds more overhead to your development process. You have to worry about things like non-determinism, like race conditions, synchronization, all of these things that you didn't have to worry about as much in the sequential version. Okay? The good news, of course, is that we are delivering tools to make it easier for you to express some of it. So expressing parallelism, coding your parallelism in your application is going to become much easier than the past. And I'll show you examples of how that's the case. So finally, you should also remember that the biggest three culprits of performance are still there. And if you take care of them, that can have significant performance ramifications on your application. So I/O, reducing the amount of I/O that you have in your application. That's a huge thing that you can do. Aggregating I/O. So a lot of I/O devices have very bad latency, but some of them have decent bandwidth. So if you can combine multiple I/Os into fewer ones, then that's usually an improvement. The other thing that you really have to worry about is cache latencies, cache locality, memory latency. Right? You want to improve the cache locality of your application. And finally, of course, you want to use efficient algorithms. Sometimes you can just win the performance game just by tackling these three sources of performance degradation. So don't forget the basics is basically what I'm saying. OK, so I'm going to show you a quick demo of the existing profiling tools that we have in Visual Studio. So I've loaded an application. This is a ray trace application. And I'm going to run it. Let's see. Oops. Fine. Yes? Visual Studio Team System has the profiler. Sorry? 2008 has the profiler, but it'll have enhancements in 2010. So I'm actually showing you basically an early version of the 2010 bits in this demo. So this is a ray tracer. And as you see, my frame rate here is about 3, which is pretty bad. Right? So what can I do in Visual Studio to try and understand this behavior? What I can do is I can go to the Analyze menu. And I can choose the Profiler option. And I can start a new performance session. So all this stuff is there today in 2008. There's nothing new here. But in case you haven't seen it, this is a good chance to do so. Under Targets, I'm going to add this ray trace application. Oops. Let's choose the debug version. And I'm just going to go ahead. There are various techniques of profiling that you can choose from the pull-down menu here. I'm going to use the sample profiler. And I'm going to go ahead and run. Oops. That's not good. Yeah. The release. I'll choose the release. Sorry about that. I was told that Murphy was taking a nap, but apparently they were lying to me. Let's just choose the release. We know that that worked. OK, so I'll start the application, run it for a while, and then I'll stop. And then the profiler will go collect the trace. It's called usually the trace is in a file called the VSP file, right here. It went ahead and analyzed the trace. And now it starts out by showing me a summary report. So the summary report shows, so some of what I'm showing you now is new. Right? Some of these things did not exist in the profiler features in 2008. So the summary page shows you the CPU utilization of this application. I'm running on a 16-way machine, and it's a sequential app, so it's not utilizing many of the CPU resources. A very cool feature of the profiler is the notion of a hot path. So this is a very nice thing. It takes you to the call stack or the call path that's responsible for most cycles in your application. You can also go and take a look at the call tree. So you can look at a breakdown of where time was spent, and it's broken down into inclusive and exclusive time. Inclusive time is the time that was spent in this function and all functions called by it. And exclusive time is the time that was spent strictly in that function that we're listing here. OK? So I don't want to go through the whole analysis of the profiling report. But I do want to show you that where most of the time was spent. If you go and analyze the report that I just gathered, you will notice that most of my time, my inclusive time, is spent in this loop. And if you look at the loop carefully, you'll see that it's iterating over the pixels on the horizontal and vertical pixels in this image that we have. And it's computing the luminance and color of every pixel based on bouncing a ray from the light source in that scene. And in this case, I believe that we bounce the ray 5 times before we finalize the luminance and color values. So this is where most of the work is in this application. Another thing that people ask us is, what about memory latency? Does the Visual Studio Profiler support cache analysis, locality analysis? And the answer is yes. The way you do that is I right-clicked on the performance session, and I opened the property page. On the left-hand side, you can choose the sampling option. And under the sample event, you choose a performance counter. And then you have access to a lot of hardware performance counters that you can sample on. So the default sampling happens on time. We take a sample every so many clock cycles. But you can also take samples every so many L2 cache misses or L1 cache misses. And we also collect a call stack. So we can also show you where in the code you're having most of your cache misses. Okay, there's a lot of cool stuff in the profiler. Right? So this is the existing profiler. There are lots of enhancements. Let's switch back to the slides. Just a quick recap of the demo. So I showed you the sampling-based profiling. And I showed you how you can collect a sample profile relatively easily. And I also showed you how you can change what you're sampling on to hardware performance counters. So you can do cache locality type analysis on your application. I did not show you the instrumentation-based profiler. The instrumentation-based profiler is much more detailed. It instruments every function. And it can deal with applications that are not purely CPU-bound. So sample profiling works well for CPU-bound apps. Instrumentation-based profiling is much better for applications that have a lot of blocking events. Another feature that I didn't show you about the Visual Studio Profiler is memory usage analysis for managed applications. If you want to learn more about the profiler and the new features in the profiler, I recommend this session that's on the screen. OK, so now I am going to switch to the new stuff. I'm going to start talking about the parallel tools. But I'm going to continue with our parallel development process, right? So now I want to start measuring performance. You want to compare your existing performance, as I said, against your goals. The way we recommend that you do this is to instrument your application, identify the phases that contribute to performance for the given scenario that you're interested in, And then we advise you to tackle the biggest problems first. It's a divide and conquer sort of strategy. So instrumentation and measurement are really critical pieces of doing performance work. And we highly recommend that you invest in the time and energy that it takes to do that for your application. The cool thing is that in Visual Studio 2010, we're going to give you measurement tools, very simple measurement tools that I'm showing in the next slide. And we have visualization tools that allow you to watch what your application is doing in time. You can also make measurements for where time is spent, et cetera, relatively easily. So this instrumentation API will be a pretty simple thing. We call it, in this case, we call it measurement block. So you instantiate a measurement block. And at the beginning of a phase that you're interested in, you just call the begin method on that object. You can specify some arguments like a string that describes the phase. This is initialization. This is phase X of my application. And then you go ahead and do the work. And then at the end of the phase, you call the end method. That's all you need to do in your application to have all of this functionality light up in the parallel performance tools. Some other stuff, some other fringe benefits of this instrumentation object is that we might collect some resource information and stash it away in the object as well. So you can do your own interrogation of perhaps CPU utilization or other resource usage during a given phase, and you can use that. You can log it, do whatever you want to do with it. So what happens when I've gone through the tuning process and I'm still not meeting my performance goals? What do I do now? So now we start a different phase of the development process, which is trying to identify areas of my application that are amenable to parallelism. Where in my application do I have opportunities for parallelism? For complex applications, this is a non-trivial problem. And you're looking really for two things. You're looking to speed up CPU-bound phases. And you're also looking for ways of hiding long latency operations from the user. So you can also meet your performance target by trying to overlap long latency operations from the user experience, hiding those from the user experience. But where and how? How do I find out where in my application I'm spending most of my time blocked on I/O? Right? Where in my application am I spending most of my CPU cycles? And we're going to show you next how you can do that with the new tools. So Visual Studio 2010 is shipping a set of features that we refer to as the concurrency analysis tools. These are going to be integrated in the profiler scenarios that I showed you, and I'll show you demos, of course, in a few minutes. These tools support managed and native apps, 32-bit and 64-bit. And they will work on Windows 7, Windows Server 2008, and Windows Vista. Let me tell you, I think we have some time for a story. About almost exactly 9 years ago, I was developing a reliable cluster runtime system. This was a system that was supposedly going to keep an application running no matter what happens. If nodes go down in the cluster or come back up, the runtime system adjusts for that and keeps your application going. So I had a terrible problem. I had a cluster, so I had a lot of network communication, which was involved. And each node in that cluster was an SMP, was a multiprocessor. And that was done on Windows NT. At the time, there wasn't remote debugging support. And there was very basic. There was no support for debugging parallel applications or doing performance tuning on parallel applications. So I had a heck of a time debugging this application. It was a really terrible experience. I wish I had the tools that I'm going to show you next. So we'll see if you guys agree. So here are the basic views that we're going to show you today. We have one view that's called the CPU utilization analysis view. What this view shows you is it shows you in time, and we'll show you markers. If you've chosen to instrument your application, we'll also show you the phases. We'll show you in time how your utilization of cores varies. So you'll see which phases of your application are CPU bound. You'll see which phases of your app have a lot of blocking. You'll see which phases are parallel. All of that stuff relatively easily. Now, the main purpose of this view is to focus your attention on an area of interest, right? You might be doing this because you're experiencing some unexpected behavior. You've just parallelized some part of your app, and you're not getting any speed up, and you want to know why. Or you could be in the process of parallelizing an app. You just want to know, where am I spending my time? And do I have a lot of CPU-bound work, or do I have a lot of I/O work? You know, what's going on? So once you've identified a phase of interest, you can zoom in on that phase and drill into that to get more details by switching to what we call the thread blocking view. The thread blocking view analyzes each thread's state in your application during runtime. It determines when your thread is running, when it's not running, and most importantly, when it's not running, why. And so we will also show you the call stack. So we will show you, for example, that this thread was opening a file. And this is how long it took to open the file. On top of that, we also show you physical disk devices. So we will show you which file you were trying to open whenever we can. So you'll get a pretty nice picture. You'll basically be exposed for the first time to the anatomy of a Windows application. You'll see exactly what's going on, which thread was scheduled when, and how these threads interact with each other. The very last thing, the last view that we're going to show you today is what we call the core execution analysis view. This is a view that exposes a couple of problems. First of all, the way it works is we show you how your threads were scheduled on the hardware resources, the cores in your system. Each thread will be associated with a certain color, and you can watch how these threads get scheduled over time on hardware. So you can detect problems like thread migration. You can actually watch your threads if they're migrating very frequently among the cores, which isn't bad for your cache performance, right? The other thing that you'll notice is if you've made mistakes, so we give you a tool called thread affinity, right? And thread affinity can help you solve some of these thread migration problems. But it's a double-edged sword. I've seen people hurt performance by using thread affinity. You'll be able to watch and see if you've made a mistake with thread affinity and you ended up mapping multiple threads on the same core while other cores are idle, you'll be able to see that. Okay? So let's go ahead and take a look. Okay. So let me close this stuff. No, thank you. So I'm going to start very basic, and I'm going to increase the complexity as we go. But it's still not going to be a very complicated application. This is a very simple matrix multiplication application that I've instrumented using the instrumentation API that I described earlier. And what I'm going to do first is I'm going to just run it. Notice that I'm going to be running the release version of the application. Notice also that I did not have to do anything special to my application other than choosing to instrument it for timing. I did not have to do anything special. Let's make sure it's built. Okay, it's built. I'm just going to go ahead and immediately create a performance session and start gathering some performance data. Okay, so I'm going to choose the concurrency feature now. Instead of the sample profiler, I'm going to use the concurrency analysis feature. And all I have to do is just launch it. Let's go ahead and do that. Okay, it was very quick. I should probably increase the... Let's take a look. So let's switch to the CPU utilization view. Okay, so this is the CPU utilization view. And what we show you in this view is we show you a few things, actually. So the green curve is your application. It's matmul2, and this is the PID of that process. We also show you how many cores in the system are idle. So on the y-axis, I'm showing you the number of cores. On the x-axis, I'm showing you time. And I'm showing you how many cores are being used at any given point in time by your application, how many cores are idle, and how many cores are being used by other processes running in my system. That's in the yellow. Right? So we believe in system-wide analysis. You cannot understand your application's performance without understanding the ecosystem that it's living in. Right? And sometimes these other applications are yours. You spawn them yourself. Right? And so part of your scenario is that you have multiple processes cooperating to do something. So the other thing that I'm showing you here is I'm showing you these vertical bars. So these vertical bars delineate these phases in your application. So that particular one, for example, is the beginning of the initialization phase of the app. This one is the beginning of the actual matrix multiplication. And this guy at the very end is where I'm generating the output file. And notice when I'm generating the output file, I'm consuming less than a single core because I'm doing a lot of blocking. Now, let's drill into this stuff and look at what, in this case, it's a single thread. So we're starting simple. This is the thread blocking view. Again, we show you time on the x-axis. We show you threads, and we show you physical disk devices on the y-axis. In this case, you can make measurements, for example. You can say, OK, how long is my initialization phase? My initialization is about 0.38 seconds. You can hover over these markers, and you will get the name of the phase that you're actually in. So that's cool. The other thing that you can do is, of course, you can let's zoom in on this I/O phase. That's kind of interesting. I'm doing I/O. And I/O, you can see this legend on the bottom right-hand side. We have a bunch of colors. These are the categories of delays that we're tracking for you. So by looking at this, and I'm used to it by now, but if you're not used to it, pink is I/O. If you hover over one of these blocking events, look at what we're showing you. We're showing you you're blocked on I/O. You made the API that caused you to block is write file. And you blocked for 8.5 milliseconds approximately in that case. Now look at this. What was I reading? Or what was I writing in this case? That's the file that you were writing. Isn't that cool? OK, so wait, there's a lot more. The other thing that we show you at the bottom is a breakdown of your thread. What were your threads doing in time? So if you look at this, in this case, my thread was spending about 90-some% of its time executing, which is green. You're basically shooting for green in this tool. And it was spending about 10% of its time doing I/O. There's some other stuff in here that barely registers. Okay? And we do this for all the threads. And we also, by the time we ship, the code that's going to do the following is not here yet. But when we ship this tool, all the statistics that we report to you are going to be based on what you're looking at any given point in time. Okay? So you drill into a place. All of the stats will be updated for exactly what you're looking at, what you're interested in. We're not going to aggregate everything and distract your attention. OK, so now let's go and parallelize this app. Let's switch back. So I've already gone through the trouble of parallelizing this the old-fashioned way. I've created threads. I'm going to set the number of actually, let me increase the size of the problem, because as we parallelize it, It's going to be very short. So let's make the number of processors 4 in, this time. Okay, now I'm going to build. And go ahead and run. So it'll take a bit longer than before because I increased the problem, and this is an order n cubed algorithm, so hopefully we won't have to wait too long. Okay. Well, okay, here we go, it's done. Okay, so let's take a look now at my report. Wow, this is shocking. Look at this. Let's switch to the CPU utilization view. What's going on? I told it to run on 4 processors, but I'm only seeing a single core being utilized. So obviously I have a problem, right? What is the problem? Let's go into the thread blocking view. Ooh, I see a lot of red. What is red? Red is user synchronization. Okay. So I have a synchronization bug, or I have some blocking that's really costly. What is that, and where is it happening in my code? Let's take a look here. It's a call to enter critical section, and it's being made on line number 56 in my application. Let's go to line number 56. And by the way, we've aggregated, sorry. Yeah. You can also see the cost of that critical section, the aggregate cost of that critical section here in these reports. So you can see here's the call stack. There were 1,536 instances of blocking on this particular API, and that's how much time it cost me across all the threads in my application. So that's very expensive. Let's go to line number, what was it, 56? No, not that one. Did I mistype? Oh, yeah, 56, sorry. 56, here we go. This is the culprit. So I intentionally put a lock there that was not necessary. But the point that I wanted to convey to you, I used to do this kind of stuff by hand. I did not have a tool to tell me how much time my application, first of all, is there contention for my lock? And if there was contention, how much time am I wasting because I'm contending for this lock? Now, you don't have to do any instrumentation, right? You didn't have to instrument anything in your app. I'm telling you, I'm giving you the answer. You're wasting that many milliseconds on this particular lock, and I'm telling you where it is in your code. So, but of course, now you have to do some work. I tell you where the lock is. Now you have to do the work. Why did I implement this lock? In this case, of course, the answer is because I wanted to demo this feature. But there's still some hard work. Don't get me wrong. We're not solving everything for you. But at least we point you at the problem, and it's relatively painless. So I'm going to, of course, this is not necessary. Matrix multiplication is embarrassingly parallel. There's no sharing. So I'm just going to take that critical section out and go ahead and run again. Again, I'm running with the release version, right? So hopefully it'll finish much faster now. And the fact that we're running the release version is actually really important. When you're dealing with parallelism, some aspects of execution, some problems will only manifest themselves when you're running the release version. The debug version will be fine, all tests will pass, but then when you start running the release version, all hell breaks loose. Oh, good, this is an improvement. Now we have, I can see already that we have more processor utilization. Good, so I am running, in fact, on 4 cores. So I'm pretty happy at this point. I can increase the number of cores in this case, and I'll see better speed up, but I'm a bit greedy. I still have 2 problems. I have the problem here in my initialization phase. So look, the actual computation phase has shrunk significantly, and now the initialization phase actually dominates my execution. So if I go to 16 processors, the matrix multiplication will actually shrink even more. But I'm also interested, I'm still not meeting my performance goals, so I have two things now. I have the initialization phase that I might be able to deal with, and I have this I/O that was happening at the end that I have to deal with. So let's see if we can tackle the I/O problem. So here's something that, these are writes. I'm used to writes being overlapped. Typically, you don't have to wait for writes, right? So why am I blocked on writes? In this case, it turns out that I actually made a mistake, another mistake, silly mistake. And I used the wrong flag on the write file API. I told it to not do any buffering. So that's going to be an easy fix. So we go to the actual I/O call. Where is it? It's towards the end here. And I'll just go and take care of that flag. Oh, the flag is specified when you open the file, sorry. So here's the flag, the culprit, is I have this no buffering flag. So I'm just going to comment this out, replace it with a 0. I trust that the OS is going to flush its buffers and persist my data to disk. I don't have to worry about that and wait for it to happen. Okay, go back now and run. So now I should see the last phase fixed. Looks like we just let's make sure that I've eliminated the I/O time that was there. Go open the thread blocking view. Sure enough, that phase is gone. You don't even, I mean, this is a tiny, tiny, tiny fraction now of my execution time, and it's all green. There's nothing that I can do about green. Green is my thread is running, so I'm all done basically. Okay, we'll come back to initialization later on. Okay, so now we have a good taste for the new parallel performance tools. What I haven't shown you are a few other features that we're working on. We have a feature that elaborates even more on things like synchronization. So sometimes you not only want to know where you blocked for synchronization, which helps you identify the synchronization object itself and where in the code it is. Sometimes you want to know the thread. What was the thread that I was waiting on? Because a lot of times you actually end up waiting excessively on a thread that was actually blocked because it was doing a lot of I/O. So in fact, you depended on I/O, not just on that lock or the event or whatever synchronization object it might be. So we're going to give you a way of tracking these dependencies. You will find out which thread you were actually waiting on, in addition to where you were blocked. And you can follow chains of these dependencies if you like to. Sometimes that's what it takes to solve the problem. And you can also find out what that thread was actually doing. So we'll give you a call stack. We'll tell you, OK, when the guy released you, this is what he was doing. So you can figure out where in the code that the releasing thread, what the releasing thread was doing when he ended up unblocking you. The other thing that we're doing is we're allowing you to analyze multiple processes. So let's say you have a process that spawns other processes, and that's an important part of your scenario. And you can't really solve the problem unless you're able to analyze all of your processes. Well, we're going to give you the ability to do that. And you don't have to run multiple times. You just collect a trace once, and we will be collecting all the data that you need in the same trace to go and analyze the other processes that you care about. And of course, we're going to give you more statistics and more guidance. There will be a lot of changes to the UI that I showed you. There will be a lot of changes to the reports that I just showed you. We still have a fair amount of work ahead of us, but I think you guys will be really pleased with what we have here. Okay, so now I've done some homework. I've identified parts of the application that are not scaling well, and I need to start parallelizing. The very first thing you need to do is, once you've identified a candidate for parallelization, is identify the form of parallelism. And there are some standard forms of parallelism that have existed for a very long period of time. These things haven't changed much, right? There's task-level parallelism. Things like multiple web requests coming at the same time. They're usually independent or mostly independent, so I can run these in parallel. There's data-level parallelism, which is something that we anticipate is going to become more popular as we have more cores. You're doing the same kind of work on many pieces of data, and now you want to be able to do these things in parallel. And there's pipelining and latency hiding, which I'm sure you guys are very, very familiar with, hiding I/O and things like that. So there are legacy programming patterns to exploit these things that we've done in the past. Things like the thread pool, I/O completion ports, asynchronous I/O APIs, things like that. Now what we're trying to do for you is we're trying to relieve you. But that was a pain. You have to admit that some of those things were a pain. Like if I'm trying to overlap my I/O, coding that stuff might be non-trivial. So what we're trying to do here is we're trying to relieve you from the painful aspects of writing parallel code. What we'd really like you to do is express parallelism. Show us what you'd like to run in parallel. And then we'll take over from that point on. And we'll do an efficient job of running those tasks in parallel. That's really the goal that we're shooting for. So now I'm going to start talking about some of these programming abstractions that we're doing. So I'll start with P-Link and with the task parallel library. I won't get into too many details here, but I just wanted to give you an idea about what they are. And then I urge you to attend my colleague Daniel Mott's presentation that's going to drill into these things in great detail. He'll also go over debugging support for these things also in his presentation. If you're familiar with LINQ, Language Integrated Query, that's in .NET, well, now you can run these queries in parallel. And all you have to do is you have to call, the syntax is very simple. You just add a .asParallel syntax to the query, and the system takes over and runs that query in parallel for you. Very, very simple stuff from a coding perspective. Common iteration loops, like for loops and for each loops. Well, now we have a parallel.for loop and a parallel for each loop. And these things will also run in parallel. All you got to do is just add the prefix, parallel dot, and that's all it takes. So again, I urge you to go see Daniel's presentation to get more information about that. On the native side, we also have a few things. So we have a concurrency runtime. We have this engine that actually does all the work behind your back to map the parallel work onto the hardware abstractions that can execute in parallel. We have what's called the Parallel Patterns Library, which is the native analogy to the task parallel library. Sorry. So things like parallel for, and I'll show you a demo in a little bit. You can run a parallel for now by just calling it a parallel for instead of a for. And there's Lambda support in the C++ compiler, so you can specify delegates, which makes the code look so much nicer. There's also a way of invoking multiple statements in parallel. And we call that the, we call that the task group primitive. So here's a quicksort, for example. So quicksort is recursive. Here I'm calling quicksort again with different pieces of the data. And I want to parallelize this. Well, I know that I can run these two quicksort functions in parallel. All I have to do in my code is I have to define what we call the task group. And in the task group, now I can run as many functions as I want in parallel. And then if I need to wait for all these things to finish, I will call a gwait, the wait method on that group. And what the underlying system will do is it will try and run all of these things that I've specified in parallel. And it will block the calling thread until all of these things have completed. And then it can continue. Okay? So it's a relatively easy way of also expressing parallelism for statements in your application. Right? Another thing that we're doing on the native side is the notion of communication through messages. Sometimes, if you have a very complicated application, it is difficult to reason about the amount of shared state that exists among all of the different threads in your application. And what you'd really like to do is you'd like to isolate the threads in a way and reason about the communication through explicit messages. Sometimes that's actually the easiest thing to do. I'm a big shared memory fan, but I recognize sometimes that shared memory is painful. It's really hard to keep track of all that memory address space and who's touching it and when. So there are 2 sessions that will give you a lot more information about this stuff. There is Rick Malloy's session, which is actually right after my session in room 408B at 3:30. And then there's Nicholas Gustafson. Nicholas is going to drill into the details of the concurrency runtime. Concurrency runtime itself has an API set that you can actually design things on top of directly. Right? So Nicholas is going to do a deep dive on the internals of the concurrency runtime. I strongly encourage you guys to attend these 2 sessions. OK. We haven't done everything for you. So there are a few things that you still have to worry about. We're working on all these things, of course, but we're not going to solve all the big problems easily. You still have to worry about some of the nasty problems in parallelism. You still have to identify race conditions. You still have to insert synchronization to solve them. You still have to worry about ordering constraints. This work has to happen before the other work, so I have to put some synchronization to order them. You still have a fair amount of work to do in order to parallelize applications. When you use these parallel constructs that I described, if you want to use a parallel for, well, you better make sure that all of the iterations in that parallel for can, in fact, execute in parallel correctly. So there are no things like loop carried dependencies do not exist. That stuff is still, all that work is still left for you to do. OK, so let's do a quick demo of the PPL. All right, so remember I was greedy and I said that, boy, I'd really like to get rid of all of these sequential phases of my application. Let me just close a bunch of these guys. And I want to go see now this initialization phase that was bothering me. So it turns out that the initialization phase was pretty basic. This is what the code looks like. It's a nested loop that's initializing the matrices, the 2 input matrices and the output matrix. And apparently, I need to parallelize this in order to meet my performance goal. So this is the parallel version of the same piece of code. The outer for loop, I've transformed the outer for loop into a parallel for. And the syntax is, this is the starting, so this is 0. This is the stopping value, which is size. This is my increment value, which is 1. And now this is interesting new syntax in C. So this is basically specifying a delegate. It's called a lambda, right? And that's it. Let's go and see if this solves my initialization phase problem. So I already have the code. I'm just going to go ahead and build it. Let's run. And let's see if we're successful. So remember, when I parallelized the matrix multiplication, I only had 4 processors running. We'll see what the runtime system does now. All right, look at that. So the runtime system, noticed that it has many more cores, and it went and parallelized that initialization phase using all of those, all of the cores in my system. Again, here's a look at the thread blocking view. Now you'll see some things that you did not create. The runtime system has created a bunch of threads, and these are the threads that it took those iterations of that parallel for loop and mapped them onto those threads behind your back. Here are the 3, so the 3 threads that I created explicitly are still there, and they take over when it's time to execute in the matrix multiplication. These 3 together with the main thread are doing my parallel matrix multiplication. Let's show you another quick example that's kind of neat for PPL. Let's close solution. Let's open that ray tracer. Remember, I told you that you should remember this doubly nested loop that's iterating over all the pixels in that ray tracer example. Well, turns out that there's a lot of data level parallelism in this code. And I'm just going to use a parallel for to solve that problem. Again, look, the code looks a lot similar to what I had before. I've just taken the outer for loop and replaced it with a parallel for. Let me go ahead and enable this code. And let's gather a let's gather a trace. Okay, so remember my frame rate was about 3. Not acceptable. Let's see what it is now. How about that? 45, 46 frames per second. And all it took was literally a minute to convert that for loop into a parallel for loop. Let's look at the profile for this guy. So, and I'm collecting a trace while this is happening. So that's pretty good speed up. That tells you that my tracing overhead is very small. Right? Okay. I just wanted to show you one important feature here, which is that we have support in the concurrency tools. And I'm trying to switch to full screen. Uh-oh. Come on. Something was bound to happen, right? Something was bound to go wrong. Okay. Let's just switch to this guy. Okay. So hopefully we're over the hump. Okay. See all this noise here? I'm showing you every parallel for loop. So you can zoom in on every parallel for loop in your program. If you're interested in the behavior of that loop, all you have to do is find it. So this is my parallel for. Zoom in on it. And if you have a lot of locks, for example, in the body of the loop, you'll be able to see how much time you're wasting contending for locks. We will show you where in the code that is. So you can also, we support TPL, and we support all these parallel abstractions in the concurrency analysis tools as well. So you can quickly sort of identify things that we're doing on your behalf, so you can go and tune them as well. This is all I had in terms of demos. Let's switch back to the presentation. Okay, so in conclusion, I encourage all of you to go and play with our bits. Most of this stuff is in the CTP. The PPL is in the CTP. TPL is in the CTP. The concurrency analysis tool is in the CTP. Some of the features that I showed you are not there yet, or they weren't there when we taped out the CTP. But go and play with it. Make sure to give us your feedback. Again, good and bad feedback. We're interested in both. Play around with the managed stuff, the native stuff, whatever you're most interested in. Definitely go to Daniel's talk. I will show links to their talks in a second before we start our Q&A session. So we have a lot of great stuff shipping in Visual Studio 2010 that we hope will make your lives easier when it's time to develop and tune parallel applications. Questions? So on this slide, you'll find basically a list of all the presentations that I referred to with the times and places. And I will be blogging soon about these concurrency analysis tools. So please stop by. Hey, questions?
Yeah, so you mentioned the concurrency analysis tools are going to require Vista or Windows 7 or Windows Server.
Yes.
What about the concurrency runtime libraries? What are the OS support for that?
I think they will go down to XP. I'm pretty sure that they go XP and up.
And are those, the availability of those tied to 2010? Will they be available earlier?
So there was a CTP, I believe, made public last year or earlier this year. Yeah, the release will be in 2010 for sure.
Okay, that was my question.
But you can start playing with them earlier.
But the final version.
You can't ship code using them.
That was my question.
Yes.
Not until 2010.
Yes.
Okay, thank you.
Sure.
Hi. Would I be able to run these concurrency profiling tools on binaries that were built in, say, built out of Visual Studio 2005 or 2008? Or does it require me to build it out of 2010?
No, you'll be able to run on any binary that runs on Windows.
Okay.
What is critical for these tools to work is accessibility to symbols. So you have to be really careful to make sure that you have the PDBs and that you've set up your symbol paths correctly for us to give you the best possible scenario, right? The best possible analysis requires symbols. That's all.
All right.
You can attach to existing apps. You can launch them. We will even give you command line tools to launch these things. In case Visual Studio gets in the way, we'll give you command line tools to do that. So.
Great. Thank you.
Yep.
Does the thread kind of zooming in things work for older binaries that are using your OpenMP library support that you have today?
Yes, the OpenMP, and basically, there aren't too many exceptions to what I'm going to say. Any application that runs on Windows, you should be able to gather a trace for. The limitations are going to be, so there are API signatures that we look for. Remember when I showed you call stacks for enter critical section? We might not have coverage for all the potential APIs that can block a Windows process, right? So in those cases, though, if we have symbols, we will show you the full call stack, and you'll be able to eyeball it and figure out, oh, that's the call that I made that eventually blocked. So if you have access to the OpenMP libraries, PDBs, you're going to be in great shape.
Okay, thanks.
Sure. Well, I'm going to be switching back and forth.
Okay, my question is, say you already have an existing application framework that's using asynchronous I/O overlapped and/or fibers that's doing stack switching.
Yes.
How will your tools deal with that? Does it still produce meaningful information?
So we will show you. The behavior of the app. If you've done a great job and you've overlapped your I/O completely, then you'll see that the threads that consume the I/O never block. But if they do block, we'll show you that they block and for how long. So sort of
What about
expose,
fibers?
we will expose the guts of the app for you, and you'll be able to see if you've done a good job, and if you haven't done a good job, why. And hopefully that's enough information to go fix it.
Okay. What about fibers when the stack switches for the thread?
Fibers, user-level threading or fibers support in Windows. You're not supposed to block. Just before blocking, you typically switch to another fiber, and those don't show up as blocking events. In this case, we're thread-centric.
Okay.
Yeah, we don't track your fibers and when fibers are blocked or not. We just track threads. Yeah.
What's the advantage of using PPL versus OpenMP? We do a lot of OpenMP. Should we now start using PPL?
That's a good question, and definitely a good question for Rick. I'm the tools guy. I'm the tools architect, and yeah, I know there's overlap.
Okay.
It might depend on your investment, right? If you already have a lot of OpenMP code base, then it's going to cost you a lot to switch. But the future might eventually be in this PPL-like programming model.
Okay, thanks.
Can the profiling be done independent of Visual Studio?
Yes, we will have command line tools that will ship with Visual Studio, so you don't have to have Visual Studio up to run the tracing.
Cool.
You will need Visual Studio to analyze the traces, however. Yep.
Okay, thanks.
Excuse me, what would be initial additional resource consumption when you run your analysis tools?
So it varies based on your application. As you saw today, even when I had a lot of contention and a lot of locking in my application, it actually was not a huge overhead. I would say less than 10% overhead is typical. But it varies. It is application dependent. Yep.
Using that Q-sort example,
Yes.
and that thing would generate threads like rabbits. Is that virtualized some way using fibers or something else? Or do those things really become threads, which would have a ton of overhead?
Not all the tasks become threads. That would be horrendous, right?
Right.
The beauty of the concurrency runtime system is you expose parallelism to it. It then decides, based on its understanding of the hardware, what is the most efficient way? What's the most efficient number of threads to create in order to run that efficiently? So it's not going to do that. If you have 4 cores on your system, it's just going to run on 4 cores, and it's not going to create more threads than necessary if it notices that CPU utilization is already peaked. Right? What's the point of creating more threads if you're already running at 100% CPU utilization? Things like that.
Does it use
it's much
the CC?
smarter than, yeah, it's not a naive implementation. It's very, very, very smart.
So we could just use this freely without having to worry about any of that?
You can?
Use this freely without having to worry about that sort of thing? That's your point?
No. My point was that you should first of all understand your application's performance. You should measure it.
Going through the right,
Yes.
pattern. But
So there's a lot of homework before you. So definitely don't use these things freely. Trust me. Yeah, someone had a hand up.
Is it also possible to run these tools remotely, like I can remotely start debugging? So I do not have to install Visual Studio on the PC.
Not in 2010. This is a feature that we would like to do for you guys, but I don't think we'll be able to get it done in 2010. Sorry. You know how that goes.
Sometimes one process requests services of another process, which sends the second process chewing up a lot of CPU. Is there any way to track that sort of correlation?
Yeah, that's the scenario that we're trying to solve for you guys. So remember when I said the multi-process scenario? We are trying to also show you when your threads block on another process, a thread in another process. And we will show you which process that is, and you'll be able to click on that process. We will have an experience for that scenario. You'll be able to basically open up the analysis for that particular process and see what it was doing that you depended on. We'll also show you the processes that were spawned or forked by your process, so you can also analyze those. So I think we're going to do a really nice job with that scenario, but we'll see. Only time will tell. Yes.
Somewhat related question is, can you launch the thread profiler from MPI?
You can definitely analyze an MPI process on a single node.
What if you want to get all the nodes, though?
If you want to get all the nodes, meet me at the parallel computing booth, and we'll have a long chat about that.
Okay, all right.
Okay?
What about static analysis and remote debugging?
Static analysis and remote debugging. As I said, with remote debugging is going to be supported for these things. Daniel is going to go over the debugger support. He's the debugger team's PM, and he'll be able to get into details. But the debugger remote features should still work with applications that use PPL or TPL.
And the static.
Is that the question?
Well, yeah, what about static? Those two questions.
Yeah. What
about
about static analysis? Static analysis for you mean the prefast, prefix, and
yeah? Are you planning any improvements to like FX comp or something to look for these types of things that you might not be able to see based on looking at the output?
So I know that in the profiling tools, they're adding some sort of guidance support. I don't think the debugger has any static analysis features for TPL and PPL. I would definitely ask Daniel Dino. I don't think we're doing anything on the managed side, native side. You can go to Rick's talk and definitely ask him. He should know on the native side, but definitely not on the managed side.
Thanks.
Sure. Yep.
Okay. As a developer, would I have to worry about setting thread pool sizes?
If you still use the thread pool, yes. If you don't use the thread pool, no. But there are some. If you use these things, you don't have.
Yeah, that's
you saw in my code, I didn't have anything that said number. When I parallelized ray tracer, all I did was I converted a 4 to a parallel 4. But there are certain cases where you will need to set limits. Right? We encourage people to design responsible applications. Don't hog the resources unless you really need them. So there are hooks to set a limit on how many threads should be created, or the maximum number of threads created by the underlying runtime system. So if your app will be more than happy with 2 or 4 cores, please go ahead and set the limit to 2 or 4 instead of eating up all the cores in the system. That's just being a good citizen. So Nicholas's talk will get into a lot of these features, a lot of these properties that you can define and set on the underlying runtime system.
Okay, thank you.
Are I'm assuming this tool is going to be basically the same for managed and unmanaged. And if it is, are there going to be any features that are, say, present for the managed code versus the native code or vice versa?
No, it'll look basically the same.
Cool.
Any other questions? Yes. Thread checker. We're working on that, but that's not part of the performance feature. This tool will help you with things like deadlocks. It's actually a really cool debugging tool. If you have deadlocks and weird ordering constraints that you're violating, you'll be quickly able to see those. But no, it won't point out race conditions. Yep. Yeah. Yeah, so we will show you network stalls as well. I don't know if we're going to have a timeline for the NICs on your box or not, but if you block on a socket API, we will show you that. So we might not have everything, but I think we'll definitely be able to. We will show that as I/O, by the way. And there's an I/O summary report that summarizes, and you'll be able to see how much time you're wasting on WinSock APIs, blocking on WinSock APIs. Yep, that's covered. Yep. No, they're not completely supplanted by this. Yes, sorry. Yeah, sorry if that was the implication. Yeah. Yes. Yes. You can analyze using this. The CTP is shipped as a VPC, virtual PC image. So unfortunately, the VPC limits you to a single processor. So you won't be able to analyze things on a quad-core or 16-way machine like I showed you here. I was just about to say that. So there is a way of, breaking loose from this requirement. I don't have time to get into it, and I don't have the details. But the answer is, if you have an existing app, yes, you can analyze it using the CTP bits. So what we do to overcome this uniprocessor limitation on the VPC is we provide you with a set of traces that we've gathered, so you can at least play around with the tool's features and see how it works by loading existing traces. You should be able to collect your own thing and analyze it. If you do it from within the VPC, it'll be a single processor. And, it's a technology preview, right? So it's not production level yet. So beta releases will be installable, right? They typically have been in the past, and I anticipate that they will be in the future. And in that case, you'll be able to install them and just run them. Yes? No. That uses the concurrency runtime underneath. I think I'm out of time. Thank you very much for coming, and thank you very much for the questions. I have some copies of Joe Duffy's parallel programming book for Windows. Whoever comes here first, I have 3. Okay. Enjoy.